All right, good morning. Happy Monday. I hope you guys had a nice week off. I know for me it like flew by, so it was exhausting. So I feel like I didn't have much of a week. But anyhow, we'll be off pretty soon for Christmas break, so we got to hang in there. Okay, so anyhow, I want to let you know that we're not going to be taking we're going to do 4 sections before we take an exam. We've already done 1-6, 1-7. I'm teaching 1-8 today, and I'll teach 1-9, and then we'll take an exam. I was reflecting over the week, and I feel like I'm giving you too much time to do assignments. I'll give you an example. With Algebra 2, the week before we left, I taught a lesson on Monday, and on Friday, they were completely lost. So I gave them a lot of time to do an assignment, and yet they were completely lost on Friday. I taught the lesson on Monday. So I'm going to really shorten things up now. So for example, I'm going to teach lesson 1-8 today. It's going to be due Wednesday night. So I'm still going to pay attention to the number of problems I'm giving you. I'm going to give you approximately 10 problems per day. So for lesson 1-8, you'll have today, you'll have tomorrow, you'll have Wednesday, and then Wednesday night at 11:49 or 11:59, it's due. So we're going to see how this works. I was also upset with you guys. I gave you a lot of time to do 1-7, and the assignment before that, only half the people are turning in assignments. So I'm gonna tighten it up now. So it's going to be like survival of the fittest, I guess. So if you want to pass the class, you're going to work. If not, then that's fine. Also, life is all about choices. So to start out today. I want to take questions on lesson 1-7. So we spent a lot of time on it, but does anybody want to ask me anything about 1-7? Teaching a new lesson today, 1-8.
Number 27.
27 on 1-7? 27, right?
Yeah.
Okay, how about if we have time at the end, I'll do it, because that's one of the harder problems and I don't want to suck up 20 minutes doing it. So I'm not going to give you that on an exam. I'm happy to do it, but I don't want to take up a lot of time right now doing it. Hold on one second, let me check something out here. All right, it's not that bad, I'll do it, but when I ask about questions, feel free to contact me anytime to work problems with you. In class though, I want to focus on the first 6 to 8 problems. I don't want to do the hardest problems because it takes a lot of time and we need to just be sure. I'm trying to, because of this distance learning, I'm trying to focus on what's important. So I'm really trying to narrow things down to keep you focused on the things that are the most important things, the things I'm going to be testing on. And I don't really want to stray off too much. Any questions that you have, like I said, I'm happy to answer them anytime, but I do not want to answer questions on the hardest problems during class. All right, 27 says to find the domain. So 27 has a square root on the top, and on the bottom is x minus 5. So they're asking to find the domain of each function. So remember that this is a rational equation. Regardless of that, this is rational because it has a variable on the bottom, which means the domain is all real numbers, except where you have a 0 in the denominator. So right away, x cannot be 5. So they're asking for the domain, and that has to be thrown out because you cannot have a 5 in the denominator of a fraction, right? Okay, now, Normally, we do not look at the numerator, but this is a rational function with a square root on the top. So it has to be considered in the domain. So if you happen to put this thing on a calculator, you would have seen that this right here, remember what I said to do, take x minus greater than or equal to 0, the radicand. So x has to be greater than or equal to 2. So that's also playing into this. So the domain then would be negative infinity. Actually, no, it has to be greater than or equal to 2. So this negative infinity is not there because this numerator is affecting the whole problem. And like I said, 1 out of a million times you're going to see this. You know, this is not like a problem I would give you on a test. Because this is not only a rational function, it has a radical in the numerator. It's a harder problem. So this means that we have to start at 2. And we're going to go up to 5 and open it at 5 to infinity. That would be the domain. So that radical in the numerator is restricting the problem. It has to be greater than 2. So this is what it looks like. And 5 has to be thrown out. All right, anything else right now? This has to be closed too. See that equal? It has to be closed. That equal. So these are parentheses and that has to be closed. If you had something that's difficult, what I would do is put it on the calculator and see what you get. You know you can't have a 5. If you're confused about this part, you can look on the calculator and the graph is only going to exist to the right of it, including 2. Okay, anything else on 1-7? Anybody have anything else on 1-7? I'm going to teach lesson 1-8, and if we have time at the end, I'm going to let you either work by yourself or you can stay and work with me. So we're looking at inverse functions. And I just want to show you what an inverse function looks like. We know the word function means it has to pass the vertical line test, but I just want to show you what I'm going to be talking about today. Okay, first of all, this invisible line is called the identity. And the reason why it's called the identity is because y equals x. In other words, when x is 1, y is 1, ordered pair. When x is 2, y is 2. When x is 0, y is 0. When x is -3, y is -3. So you notice that the x's and y's are equal and it creates this line. Now, the thing about an inverse is that it reflects over the identity. So for example, if I drew an exponential growth function, the inverse flips over the identity. So it would look like this. So if this was exponential growth, the inverse is a logarithm. In other words, if this function was f of x equals 2 to the x, the inverse would be log base 2 of x. Because it flips over the identity. It reflects over the identity. And one more thing, this is kind of just a preview of what we're going to get into. This point right here, which is 0 up 1, This point is right 1, 0. So the points just switch. So if you're ever trying to find an inverse of a graph, just switch the points. So instead of 0, 1, it'd be 1, 0. If you had like right 1 up 3, this would be right 3 up 1. So you just switch the points to get the inverse. So this is just a part of what I'm going to be talking about today. So there's 5 objectives today, and I'm going to go through all 5, and then I'm going to take questions if you have any. So the first thing we're going to look at for objective 1 is verifying inverse, and verify means prove. So let me just say this. To verify inverses, you're going to look at the composition. And I taught you this in the past, and if you don't know how to do it, you're not going to be able to do this. So this composition has to equal x, and when you do g of f of x, it has to equal x. And if this condition exists, then the functions are inverses. I'm going to show you an example in a minute. Let me make some notes though. So the first note is that the inverse of a function is written f inverse of x or f inverse. So you do not read it as f to the negative 1. You read it as f inverse of x. This doesn't mean flip it to the bottom. So remember in the past, we said that x to the negative 1 means 1 over x, negative exponent rule. Okay, I'm not talking about that in this section. So we're not talking about this at all. We're talking about a special notation called f inverse. And I also want you to know that sometimes you'll see it written like this. F of f inverse of x equals x, and f inverse of f of x equals x. Now, most of the time, you're going to see me write it like this to eliminate confusion, but I do want you to know these mean the same thing. So whether you see me write it like this, or whether you see me write it like that, G is lots of times looked at as the inverse. Okay? So don't get mixed up with the notation. This notation means the same as this notation. So these are the same. So let me do a problem. So they're going to ask you to verify inverses, or verify that they are inverse functions. So they're going to give you a function. This one's a line. And then they're going to give you another function, which is a line. So that's not rational, right? That doesn't have a variable on the bottom. That's a line. That's also 1/3 x minus 2/3. So to prove that these are inverses, to prove that they reflect over the identity, you're going to prove this equals x, and then you're going to turn around and prove that this equals x. But first things first. So remember how to do this? You drop the f down and put the g function in. And that becomes the x of the f function, 3 times something plus 2. And the something is x minus 2 over 3. So the 3's cancel. You get x minus 2 plus 2 equals x. So that worked. Now this cannot equal any number, it has to equal x. Now, if you did that and it doesn't equal x, they're not inverses. It has to equal x. So now that it did equal x, that was the first part of the proof, we do this. So now we put g and the f of f. That becomes the x of the g function, which is something minus 2 over 3. And the something is 3x plus 2. So those 2's cancel. You get 3x over 3, which is x. That worked. Therefore, these are inverses, and we proved that they are inverses. So we proved that this composition equals x, and that composition equals x. Therefore, those do reflect over the identity y equals x. Okay, I'm only going to work one example for each section. If we have time at the end, I'll work more problems. Does anybody want to ask me about anything that's on either board right now?
Yeah, I have a question.
Good.
So if, say one, the f of x, yeah, that one, say that one didn't equal x, then you would just like stop.
Stop. Yeah. Thank you for bringing that up. Right. Let's say that this thing equals x squared. You're done. They're not inverses. So if this thing equals anything but x, like let's say it equals 2 or 0 or x, you could just stop. Don't even do that other part. Just say, they're not inverses. Let me give you another clue. Let's say this was a line and this was a quadratic. Could those be inverses? Can a line ever reflect to give a quadratic?
No.
No. So you wouldn't even do the problem. You would just say, this problem is ridiculous. A line is never going to have an inverse. It's a quadratic. Done. Stop the problem. I mean, that's what I would do. I wouldn't do any work. If I saw a line in a quadratic's never going to be the inverse of a line. So I would just write to the teacher or write on the test, a quadratic is never going to be the inverse of a line, and circle your answer and be done with it. Right?
Right.
Thanks for bringing that up. Yeah. If that fails right there, don't do the other part. Okay, anything else before I erase this? Okay. So if you guys know how to do the compositions, that part's going to be easy for you. If you don't know how to do the compositions, you either need to meet with me or meet with somebody else to show you how to do the compositions, because I taught that in the past. Okay, the next thing is easy. We're going to find an inverse. And here's the steps. So the first thing you're going to do is you're going to replace f of x with y. The second thing you're going to do is switch x and y. The third thing you're going to do is solve for y, or isolate y. And the fourth thing is you're going to change y to the new notation f inverse of x, just to show that it's an inverse. So I'm going to do 3 examples. One's going to be linear, one's going to be a cubic, and one's going to be a rational function. So here's the linear one. And I expect everybody, even if you have a 1% in here, I expect you to be able to do this. So we're going to replace, switch, solve, and change to the notation. So we're going to take that out and put a y in. We're going to switch x and y. We're going to solve for y or isolate y by adding 5, add 5, and divide by 7. Fernando, I need you to mute yourself. Fernando. So we get y is equal to x plus 5 over 7. And if they asked us to graph, we would split it up, but they're not asking us to graph. So don't split it up, leave it like that. So change y to the notation to denote an inverse and leave this alone. So pretty easy. Replace f of x with y, switch x and y, isolate y or solve for y by adding 5 to both sides, divide by 7, and then change y to the notation for inverse. Pretty easy, right? Okay, this one's a little more complicated. It's a cubic, so let's take a look at it. Can I erase this? Can I erase this? Yes.
Yeah.
Okay. Now this is the cubic. This is a graph up 1, but we don't care about the graph right now. All right, so we're going to find an inverse. So we're going to replace f of x with y. We're going to switch x and y. We're going to solve for y, which means subtract 1 from both sides. Okay, now, this is not a square. If it was a square, we'd take the square root of both sides and put plus or minus. We're not doing that. Okay, well, I'll do it in a different color. What we're going to do is we're going to take the cube root of both sides. And remember, when you have an odd index, don't put plus or minus. So since we have 3 y's under there, 1 y gets to come out. In other words, when you have the index matching a power, 1 gets to come out. So change it to the notation f inverse of x is equal to the cube root of x minus 1. So isn't this interesting, you guys? This guy looks like a snake, and his inverse looks like the sideways snake. Makes sense, right? This guy's going up and down, that guy's going to go left and right. But we're not graphing right this second. Any questions about this? You guys okay? Can you guys unmute yourself? Somebody talk to me, please.
Yeah.
You guys okay?
Yeah.
Okay. Okay, now this last one I'm going to do in finding an inverse is going to be a rational function, so watch this one. See the variable? That's rational, right? We don't know what the graph looks like, but who cares? Okay, we know it's a rational function. All right, so we're going to change f of x to y. We're going to switch X and Y. So now we have a Y in the bottom. I'm going to isolate Y by subtracting 4. And now you can do one of two things. You can multiply both sides by Y, or you can cross multiply. Now let me show you what I'm going to do. I'm going to multiply both sides by Y, and I'm not going to distribute. And the reason why I'm not going to distribute is because I want to isolate Y. Right? And that is the inverse. All right, you guys, that's how you find an inverse. And this makes sense. And I have confidence this is right because I started with the rational function and I ended with the rational function. So it's not like I started with the rational function and ended with a line. Right away, we know we did something wrong because the inverse of a rational function is never going to be a line. Okay, now I'll come back and work some more problems if you want me to, but that was objective 2, finding an inverse. Okay, the next objective has to do with using the horizontal line test. Now, I did not say the vertical line test. I said the horizontal line test. This is different. All right, check this out. We know the vertical line test checks for functions, right? So we've looked at quadratics and said they're functions because they pass the vertical line test. But this is the horizontal line test. So what is it? So let me write this down. A function f, or f of x, has an inverse function if no horizontal line intersects the graph of f at more than one point. Now that's confusing. So let's take a look at a picture. So we want to know if this function has an inverse. Let me say it better than that. Which function has an inverse function? So for example, if this was your graph, that is a function because it passes the vertical line test. But if you hold your pencil sideways like this, it only crosses my pen once, right? Crosses once, crosses once, crosses once, crosses once. So what that means is that this graph is 1-to-1, and it means that the inverse is a function. So let me repeat this. So this graph is a function because it passes the vertical line test. But if it passes the horizontal line test, it means its inverse is a function that passes the vertical line test. Watch this problem. Okay, we know that the parabola is a function. It passes the vertical line test, but watch this. This passes twice. Let me just draw a picture of the inverse. The inverse, when reflected over the identity, looks like that. And guess what? Because it fails the horizontal line test, the inverse is not a function. So the parabola is a function because it passes the vertical line test, but because it fails the horizontal line test, the inverse is not a function. Okay, this is the sine curve in trig. The sine curve passes the vertical line test. It's a function. But it fails the horizontal line test. See how it's passing through my pencil twice? So therefore, its inverse is not a function. And when we get into trigonometry, we're going to have to restrict the domain in order to create an inverse because the inverse is not a function. Now, I'm just going to make a little note here that if a function passes the vertical line test, passes the horizontal line test, it's called one-to-one. And what that means, ladies and gentlemen, is that no y's repeat. So remember with the function that no x's could repeat. And now I'm saying if a function passes the horizontal line test, it's called one-to-one, and that no y's repeat. So basically we use the horizontal line test to see if the inverse is a function or not. Okay, so objective 4 is use the graph of a one-to-one function to graph its inverse function. Now, remember what I said about this. I said that a graph of a one-to-one one-to-one function f and its inverse reflect across the identity which is y equals x. So let me show you what I mean. So I introduced it at the beginning of this lesson, and now I'm going to show you what I'm talking about here. So here's what I'm saying. Okay, let's say I have this graph, and I'm going to actually graph this because last period I didn't do it and it turned out bad. Okay, that is a function, right? It passes the vertical line test. And I'm just going to draw the identity y equals x here. So this is y equals x. This says a graph of a one-to-one function, and it passes the horizontal line test. So that is one-to-one. And its inverse reflect across the identity. So check this out. This point is left 2 down 1. This point is left 1 up 3. And this point is right 1 up 1, 2, 3, 5. If I just switch those points, aren't I going to get the inverse? Because when we found an inverse, didn't we switch x and y? So watch this. What if I graph left 1 down 2? What if I graph right 3 down 1? And what if I graph right 5 up 1? Doesn't that give me the inverse? Doesn't the black graph reflect over the identity to give the orange one? So all we do is switch the points. That was easy. And I'm not artistic, so for me not doing that, I'm just trying to reflect it over, it's really hard for me to see that. I'm not a visual person in that way. So I can just switch the points. I can just switch x and y and get the inverse. So let me just reiterate some of the things I'm saying here. So I'm saying that if you use the horizontal line test, first of all, you know this is a function. It's a function. It passes the vertical line test. If I use the horizontal line test, we know that this guy has an inverse function. See that? He's a function too. Because he passed the horizontal line test. That means the inverse is also a function. And I think I showed you this one earlier, but I'll show you again. This is an exponential growth function. So if you graph this, you could put in a 0 up 1, put in a right 1 up 2. So this is exponential growth. If we were going to graph the identity, what would the inverse look like? Well, this point is 0 up 1, and this point is right 1 up 2. So what if I just switch the points? What if I say, okay, well, I'm going to graph right 1, 0 now, and I'm going to graph right 2 up 1, and if I reflect the identity, doesn't it look like that? Well, guess what? This is the logarithm, and he is the inverse of exponential growth. See how the points just switch? So what were we talking about? Well, this guy is a function. He passes the vertical line test. This guy also passes the horizontal line test, which means his inverse is a function, and we know he's a function. Okay, any questions about this? Well, you're either completely confused, right? Or you're with me. This is the hardest thing for me. Well, one of the hardest things with distance learning is that I can't see you, you don't respond to me, and I have no idea what's going on. Like, are you there? Can you hear me? Is anyone listening? Does everybody understand, or is everybody lost? The last objective is it's pretty comprehensive. You have to do a lot of things. You have to find the inverse. you have to graph f and the inverse, and you have to state the domain and range of both. So I'm going to try to keep this real organized, and this does build on what we've done in the past. So they give us the quadratic, and the quadratic is shifted down one, and they also restrict the domain. So this is the domain. It says the graph only exists to the right of 0. So I'm going to graph this first over here. And I'm going to graph the identity just as a roadmap. So if you need to draw the points on this or state the transformation, that's how we did it. So the parent points are left one, up one, 0, 0, right one, up one. And this is saying down one using transformations. So down one means 0, down one means -1, down one means 0, and you graph those. So left one, 0, 0, down one, and right one, 0. Now, this only exists to the right of 0, so this graph is going like this. So the domain is restricting it to the right of 0. So this is the graph of f of x. Okay, now, they want us to find the inverse. So you know the steps. Change f of x to y, switch x and y, solve for y, add 1. So it'd be x plus 1. Take the square root, and don't forget plus or minus. Now, which one is it? Well, if we restricted the domain here, we have to restrict the range here. Remember, you have to switch them. So f inverse of x is equal to the positive 1. You guys see that? So like I said, if you restrict the domain here, you have to restrict the range here. So it's not plus or minus, it's positive. So now, remember the points for square root are 0, 0, and right one, up one. And this is saying left one. So left one would be that, and left one would be 0. And I know I'm right. Because look, those points switched, and those points switched. Hold on a minute, 0, 1. Left one, 0, 0, 1. Yeah. So the reason why you don't see these points, because we had to throw them out of the domain. So see how they switch, left 1, 0, and 0, 1. So I know I'm right. So let's graph these. Left 1, 0, and 0, up 1. And remember, this is just this is square root. That's been shifted left 1. So that looks like a reflection over the identity, right? So the domain of f and the range of f, the domain is the black for f. It's to the right of 0. So it'd be closed on 0. to infinity. The range would be closed on -1 up forever. And the domain of the inverse and the range of the inverse, the domain would be to the right of -1, and the range would be closed on 0 to infinity. Now notice what happened here. Look at how the domain became the range of the inverse and the range became the domain. So they switched. So the ordered pairs didn't switch, but the domain became the range and the range became the domain. Okay, so they asked us to find the inverse, they asked us to graph, and they asked us to state the domain and range. Okay, now that is the lesson. I did teach everything. And here's what we're going to do now. Well, would you want me to do another one of these first? Would you like me to do another one of these problems?
Yes.
Okay, how about I do number 46? So see how this is requiring previous knowledge? So it's requiring that you know how to do transformations. It's requiring that you can do compositions. So it's requiring a lot of previous stuff. So if there's something you don't understand, you either need to work with me or work with somebody else, because the math, as you already know, keeps building on itself. So I'm going to do 46. So on this on page 270. So the function is x cubed plus 1. So we know the cubic looks like this, and this is up 1. So I'm going to graph this first. So the points are left 1, down 1 of the parent, 0, 0, right 1, up 1. And if we go up 1, the x is not, the x isn't affected. So up 1 would make that a 0, up 1 would make that a 1, and up 1 would make that a 2. So let's graph the function. I'm going to graph the identity too. So the function is left 1, 0, 0, 1, right 1, up 2. And this looks like a snake. So he's going to look like that and like that. And this is f of x. So they want us to find the inverse. So we change f of x to y. We switch x and y. And we solve for y. So subtract 1, and you're not going to take the square root. You're going to take the cube root. Do not put plus or minus. You only do that when you do square roots. So you have 3 y's, and it matches the index, so a y comes out. And this is the cube root. And doesn't this make sense that this guy's inverse is the sideways snake? So his points are the same as the cubic. His points are left 1, down 1, 0, 0, right 1, up 1. And this says to go right 1, So right one would be 0, right one would be 1, and right one would be 2. And I know this is right because look at these points and look at these points and look at these. They're exactly switched, right? So I know I did it right. So 0 down 1, right 1 0, and right 2 up 1. And we know that this orange guy is a sideways snake, and he's only been shifted right 1, so he's still sideways. And doesn't that look like it reflected over the identity? And I'm lucky that I know math because that would have been hard for me to draw and actually visualize. I'm not a visual artistic person. So I'm more math where, okay, I know the inverse, the point switch, the ordered pair switch. And by just doing the math, I came up with the reflection over the identity. Okay, so let's do the domain and range. So the domain of F is where the graph exists left and right. So it exists forever left and right. The range is where the graph exists up and down, forever up and down. And the domain of the inverse and the range of the inverse, the domain is forever left and right, and the range is forever up and down. So the graphs would be the B part of the question, and the domain and range would be the C part. All right, now class is over at 12:10, but I'm going to give you the option to leave on your own and work on the assignment, or you can stay with me and ask questions, or we can work some more problems. Of course, when I let you go right now, you can play Xbox, go walk the dog, make breakfast, whatever you're going to do. So there's no way of me telling that you're doing the assignment, but I'm giving you time to do it. So life is all about choices. So you either work on the assignment that I'm giving you time for until 12:10, or make a decision to do something else. But right now I'm going to turn off the recorder. And if you want to hang out with me and ask questions, or I can work more problems, you're welcome to do that. So this is going to be not as formal. I want to be able to just work with you like a group with me. So let me turn the recorder off. Those of you who want to take off, have a good day. Those of you who want to stay with me and work some more problems or have questions, feel free to do that.